Okay, so this is the first problem for the chapter number 12 assignment. So in this chapter we're starting to look at kinetics, where we're dealing with forces and then using that force to find accelerations, and then we can use what we learned in the last chapter to solve the problems. So this first problem here, we have this tugboat, and we're given an equation for force here that changes with velocity. And the question wants us to find the time required to increase the speed from an initial value of 1 meter per second to a final velocity of 2.5 meters per second. And so in order to solve this, the first thing I did was just sketch a quick free body diagram, and that helps us recognize that all the forces in this problem are in one direction, in the x direction. And so then I wrote the main equation for dynamics here, force equals mass times acceleration. And we're given the equation for force, so we can substitute that in for force. And then on the other side of the equation here, we're given the weight. And so to change from weight to mass, we can divide by our gravity. And so that gives us the mass for this problem, and then that's times acceleration. And so we can take this equation and solve it for acceleration, and that's what I have here with these decimals. And then once we have that, we use some of the equations we learned from chapter 11 because we want to go from our acceleration to velocity. And so we know that ax equals dv dt. And then we rearrange that and we solve for time, because that's what the question wants us to find. And so integrating that on the left side here, our bounds are from 0 to t, and after integrating that and plugging in our bounds, we just get t. On the other side here, we're integrating with respect to velocity. So for our bounds, we can put in the velocities given in the problem, the initial and final velocity, v2. And then we just integrate that. And that's what we have here. There's kind of a U sub or chain rule there. And then we plug in our bounds, and that gives us a time of 18.84 seconds. And so that's the answer for part A. And then in part B, we kind of need to look back to the chapter 11 ideas. So we have this relationship here that relates position and velocity. And so we can rearrange this equation similar to what we did above, and then integrate for position on this side and velocity on this side after we've got like terms on the same side. And so integrating this side, similar to time up here, we get that just our position equals our integral from 1 to 2.5 of v times 1 over acceleration, and we can just plug in the equation from acceleration that we found above. And so integrating that, we find that for part B, the distance traveled during that time interval up to this 18.84 seconds is 36.138 meters, and so that's the answer for part B. Okay, so for problem number 2 here, we have a diagram here of this truck, and it's pulling this boulder up, and it can be easy to miss, but looking closer you can tell that this boulder actually is hooked to a pulley system here that we're going to have to take into account when we solve this problem. And so the first thing the question wants us to know is the horizontal force between the tires and the ground. So as this truck pulls this boulder up, what is the force between the ground and the tires? And so to start with, I drew a free body diagram of here, and so we can see that there's 4 forces. There's the weight of the truck, the normal force pushing back, the force of the truck pulling to the left, and then this friction here, or the horizontal force that the question's asking about. And then we can set the kinematic or the kinetic diagram here, and that simplifies down to mass times acceleration in the x direction as the truck pulls to the left. And so to solve this problem, I first wrote down a lot of what the question gives us. It gives us the acceleration of the truck, which is the 1 foot per second squared. And it also gives us the pound weight of the truck and the pallet and the boulder. And so going back to our equation, force in the x, the sum of the forces in the x equals mass times acceleration in the x. We can write an equation for the free body diagram of the truck that we have. And so that's what I have here. And then when doing this, we have to recognize that this mass is not the pounds of the truck. It's actually, we need to divide by the acceleration here of gravity to convert it to slugs. And so converting that, we have this equation here, but that still has 2 unknowns in it. So we're going to have to find another equation from the boulder at B. And so drawing another free body diagram here of the boulder in that little triangle with the platform under it, we can see that we have 2 tensions pointing upward and then the weight pulling down. And that's the combined weight of both the boulder and the platform. And then that can equal this diagram here. And so looking at this relationship, there's 2 tensions here and only 1 up at the truck. And so we can relate that to find that the acceleration difference between the truck and this boulder, the boulder is 1/2 the acceleration of the truck. And so using this, we can create an equation in the y direction, which I've done right here. And then this only has 1 unknown, the tension, but we've had to put in 2t because there are 2 tensions because of the pulley. And so solving this, we can find that the tension is 609 pounds. And then we can plug this back into the above equation, and this will allow us to eliminate one of our unknowns and find the force on the tires there. And so that is the first part that the question wanted us to answer, and that comes out to 765 pounds pulling to the left. The truck's pulling to the left. And so then for part B, the question wants us to find the force between the boulder and the pallet. And so I did another free body diagram here, and so basically we're looking for the normal force pulling up. And so we have to use a different weight for this problem. We're kind of ignoring the weight of the pallet here, and we're only concerned about the weight of the boulder, the 1,000 pounds. And so going back to our second rule from Newton, force equals mass times acceleration in the y direction. We know in the y direction we have the normal force pulling upward and the 1,000 pounds of the boulder pulling down. Our mass we can calculate right here. To convert that to slugs, it's the 31.055, and then our acceleration is 1/2 foot per second squared because of the relationship to the acceleration of the truck that was given in the problem. And so in this, there's only the 1 unknown, what we're searching for, and so solving this equation, we can find the force between the boulder and the pallet comes to 1,015.53 pounds. Okay, so for problem number 3, we have these 2 people here that are playing tetherball. And the question wants us to find the angle theta that the chord forms with the pole BC. And so looking at the diagram they gave us here, the theta angle is actually up here. And so I started by just looking through the problem and recognizing what was given, and then I drew this free body diagram here. And I decided to solve this for alpha. That's the angle I put in here, and then using a relationship there we can find the angle for theta that it's asking for. And so looking at our free body diagram, we can write an equation for the forces in the x and the sum of the forces in the y direction. And so the sum of the forces in the x, all that's in the x direction is the component of our tension. which is t cosine of alpha. And then that has to equal our mass times acceleration. And our mass converted to kilograms is 0.45 kilograms. And since we know that this is a normal acceleration pointing in towards the center of the circle, we can replace that with v squared over rho. And v squared was given to us in the problem. That was the 4 meters per second. And then for rho, we don't know that, but we are told that the length of this cord or this rope is 1.8 meters. And so I drew this triangle here, and using some trigonometry, we can create a relationship there. So we know that after solving that rho equals 1.8 cosine alpha, and we can replace that unknown variable in this equation. But looking at this equation, we still have two unknowns, and so we can do the same thing in the y direction. And so the sum of the forces in the y direction, we have the vertical component of tangent, which is sine alpha times tension. And then we also have the weight pulling down, which is our 0.45 kilograms times 9.81. And then since we know that the ball is not accelerating up or down, we know that the acceleration in the y direction is 0. And so we can solve that equation in the y direction for our tension, and then replace that into our equation up above. And now we have an equation that only has the angle alpha in it. So I rewrote that up here to be able to solve it. And then rearranging this equation, we know that cosine squared alpha over sine alpha equals 0.906. And then using a trig identity, we can turn this in the top of this equation into 1 minus sine squared alpha. And then continuing to solve this, we can come up with an angle for alpha of 40.1499 degrees. And then the question wasn't asking us for alpha, though. It was asking us for theta up at the top by b. And so we know that all of the angles in a triangle have to add up to 180 degrees. And so subtracting off the 90-degree angle here and alpha, we can find that theta is 49.85 degrees. And so that's it for part A. And then on part B, we have to find the tension in the cord. And we can use the equations that we've already created and just plug in our found value for alpha. And so plugging in alpha into this equation and replacing our rho again in terms of alpha, we can solve this and find that the tension in the cord is 6.85 newtons. So for problem number 4 here, we have this wrecking ball, and the problem wants us to find the tension in the cable of the wrecking ball at these different locations. So for this problem, I decided to use the natural or the normal tangent coordinate system. It seemed to fit really well. So we know that the force equals mass times acceleration in both the normal direction and the transverse direction. And so the first thing I did was draw a free body diagram of this wrecking ball at C here. We drew the tension going off with that angle of 20 degrees up here, which means this angle here would be 70 degrees. And then our weight is pointing straight down. And then I also just drew on our coordinate system and a little direction there that shows that up and to the right is positive on this. And then I drew this diagram here for our mass times acceleration and set those equal. So in this problem, the first thing we had to recognize is that at point C here, the problem tells us that the ball is at its highest point, which tells us the velocity there would be equal to 0. And since we know that this equation holds true, we can also say that the acceleration in the normal direction is also 0, or towards the center, towards A. And so setting up our equation, force equals mass times acceleration in the normal direction, and setting that equal to 0, we find that we only have one unknown, which is the tension, which is what we're trying to find in this problem. And so we can simply plug in our weight there, our force of 130 pounds, and then take the cosine of that angle, and that gives us a tension at C here in our cable of 122.16 pounds. Okay, so for problem or part number B, we have a little different situation, so I redrew the free body diagram here. So at D, we know our tension is going straight up. We're at the very bottom of the swing, and we know what that's equal to. And so since we don't have any forces in the tangential direction, I decided to draw or write an equation for force in the normal direction. And so we have our tension minus our weight pulling us down, and that has to equal mass times acceleration. And then substituting in what we know acceleration in the normal direction is into this equation, we have everything we need to solve this, because we were told that the tension or the cable was 45 feet long, so that will be rho. We're told the speed there, so we have that. And we also have the weight, and so dividing the weight by 32.2 and then putting the force of 130 pounds on this side, we can solve for the tension at the bottom of the swing, and we get that is equal to 145.6 pounds. On this problem, we're given a turntable here, and the first thing that sticks out to me on this problem is that the problem tells us that the acceleration in the tangential direction is constant, and it gives us a value of that. So that's an important piece of information. So since it says constant acceleration, we know we can use this equation here that works for constant acceleration. And then drawing a free body diagram here, we can look at that and pull out the directions that these forces are acting in and where those components of acceleration are acting. And so solving this, we can get that the final velocity was 2.4 meters per second. That's just plugging that into this equation up here. And then to solve this equation, what I did was I solved for force, the force on this block on the turntable, in two different ways. And then I was able to set those two equations equal to each other and solve for our coefficient of static friction. And so looking directly into the turntable flat, we have this little diagram here, and we know that the normal force pointing up minus the weight is the only forces in that y direction. And so looking at that, we know that that has to equal 0 because there's no acceleration up or down on the turntable. And so that tells us that our normal force has to equal our weight. And we know that our weight is our mass times the acceleration of gravity. And so plugging that in, we know that our force also has to be mu times n. That's just our equation that helps us find the static friction coefficient. But in order to solve this, we need to know what the force is equal to. So up here, I created another equation for force. So we know that our force is mass times acceleration in the tangential direction plus mass times acceleration in the normal direction. And then substituting in what we know, the acceleration in the normal direction is v squared over rho, which rho was given to us in the diagram up here, and we solve for our velocity here in the first step because it's a constant acceleration. And our acceleration in the tangential direction was given to us, and so all we were missing here is mass and force, and those are the equations that we needed to use. And so setting those equal to each other, like what happens on a lot of these problems, the mass actually cancels, which is surprising, but often the mass does not play a role in these calculations. And so plugging in the values that were given and that we found that I stated, we can cancel out the mass, and that only leaves us with one unknown, mu s. And so just solving that equation, we get that the coefficient of static friction for this problem between this trunk and the turntable here is the 0.236. Okay, so this is problem 6 here. And looking at this problem, it tells us that we have Venus orbiting the Sun. So I drew a little diagram here of this is Venus and it's orbiting the Sun. And the problem tells us that the velocity of Venus going around the Sun is this constant number here. And so that, thinking about that, we know that velocity is always tangential. And we also know that if this velocity is constant, that means we have zero acceleration in that tangential direction. And so because we know that, we can just set that equal to 0. We know that our equation for force is mass times acceleration in the tangential direction plus mass times acceleration in the normal direction. And so we can cancel out this because our tangential acceleration is 0, and we can replace this with our normal acceleration from our equations. And so that gives us one equation for force in this problem. The other equation for force comes from what we know about planetary gravity and the equation we use for that. So we know this equation here holds true, and we know that this big G gravity is a constant that we can use. And so taking this equation, we're looking for the mass of the Sun, so we don't know that. We also don't know the mass of Venus yet, but we end up not needing that. And then this is the radius that was given to us here, rho. And so, since we have two equations for force, we can set these two equations equal to each other. And like I said before, the masses of Venus cancel. And then we have everything we need to know to solve for the mass of the Sun. And so we have to change the units that we're working with to match our gravity constant here. We need meters, kilograms, and seconds. And so converting those and plugging that into our formula here, we can get that Gm equals this, and then since G is a constant, we can just divide that out and find that this is the mass of the Sun, which is part A. And then for part B, the question wants us to find the acceleration of gravity at the surface of Sun. So basically that's like the lowercase g that we use in a lot of our calculations when we're working with things that are close to the Earth's surface where we can treat gravity like a constant. And so going back to our equation here for the gravity of large objects in the solar system, we can replace our force with mg. So we're looking for this little g close to the surface of the Sun. And once again, the little masses will cancel. The m here is the mass of the Sun, which we found from part A. G is our constant that we can plug in, and the radius of the Sun was given to us in the problem. And so plugging all of that in, we can solve for the little g, and we get 276 meters per second squared, which is a really big number compared to the gravitational constant that we're used to using on Earth. But that makes sense because the Sun is so much larger and has so much more mass than the Earth. So that's all for problem 6. On this problem, we're not given any actual values or numbers to plug in. What the question wants us to find is the relationship between the force and the distance. And so we're supposed to show that F, the force, is inversely proportional to the square of the distance r from the particle center here. And then the problem also gave us this equation here. And so to start with, I just wrote down a couple of the equations and relationships that we have learned in this chapter. So we know that U is inversely proportional to R. And we also know that this is the equation for gravity in this situation. And so looking at this, we just need to start manipulating the equation until we can find the relationship that we're looking for. And so looking at this equation, we can replace this r squared with a u squared in the numerator. And then we are given this equation here for r. And so we know that if u equals 1 over r, then u equals 1 over this as well. And so all we have to do is reciprocate this fraction here to get what u is equal to. And then using that, we can try and find this piece here, the second derivative of u with respect to theta. And this is a pretty simple derivative because it is with respect to theta instead of with respect to time. And so the bottom here is just a constant. We take the derivative of the numerator and we get sine theta. And then we take the second derivative again. The derivative of sine theta is cosine theta, and so we have this part of the equation here. And we also have u for this part. And so taking those, we can plug those in, and the cosine thetas will cancel out, leaving us with this equals 1 over r naught. And so what that can allow us to do, 2 over r naught, excuse me. So once we found this relationship on this part here, we can multiply this over here. These are all constants. This m and the h are our constants, which leaves us with this equation here. And we know that u squared is, once again, 1 over r squared. We've used that relationship quite a few times. And then just rewriting this, we have this is our final equation here. And we can see by looking at this that our force is inversely proportional to r squared, which is what the question wanted us to find. Okay, so on this problem, we're given the diagram of the Earth here. And there's a satellite that can rotate, orbit the Earth in 3 different ways. So the middle one here is an elliptical pattern that the satellite would orbit. This one here is the circular path, and then the one up here is the escape velocity when the satellite's moving fast enough that the pull from the Earth is not strong enough to keep it orbiting. And so the first thing the question wants us to find is the increase in speed required at point A for the satellite to achieve the escape velocity. And so the problem tells us that currently the satellite is following this path of the circular orbit, and it tells us the altitude. And so we need to find out the velocity that keeps the satellite in this path that it's on now, the current velocity, and then find the difference between that and the escape velocity. And so we have this equation here for the circular velocity and this equation here for the escape velocity. And we need to find each of those values and then find the difference between them for part A. And so the first thing I did was find out this part of the equation because it's found in both. So g is our constant for gravity, which is here. And then the mass of the Earth is this number here. And so that comes out to 3.98 times 10 to the 14th for this part of those equations. And then the bottom of these equations is the radius A, and that's from the center of the Earth. And so RA, we have to add the height here plus the radius of the Earth. So adding those two together gives us a value for RA. And then that needs to be converted from kilometers into meters to work with our equations here. And so using that information, we can calculate the velocity of the satellite in the circular path and the escape velocity needed. And finding each of those, this is what I found. And then taking the difference between these, the answer to part A is right here. And then for part B, it's a similar idea, but we want to slow down the velocity of the satellite to get it to travel in this elliptical path here, the inside ellipse. And so the first thing we needed to do was find out, I called it RE for ellipse, and the radius of that, similar to RA, we had to add those together to get that value. And then we had this equation here, and looking at these two equations, we can recognize that the difference between the angle cosine A and cosine B is 180 degrees, and so we can replace cosine theta B with a negative cosine theta A in that equation. And then adding these two equations together, this is the equation that we get. We know these two values here, and GM was calculated up above. And so plugging all of that in and taking the square root of it, we can find the value of H in this equation, which is right here. And then what we needed to find was the velocity A here, which is for the ellipse. And we know the equation for that. And so that gives us that velocity, and then we can take the difference between that and the velocity up above for the circular path, which gives us this change in velocity of 725 meters per second, which is pretty small compared to some of the other values we've been getting. And then part C, the final part of this problem, the problem wanted us to find the eccentricity, E, of the elliptic orbit. And so to find that, we have this equation here, and we know everything in here from our previous calculations except for the eccentricity value, which we're trying to find, and the value for C. And so first thing we had to do was rearrange some of our equations and then plug in our radiuses to find our value for C, which is here. And then all we had to do was plug that in here and solve for E. And so E comes out to 0.33. So this is problem 9, the last problem for this homework set. And this is another one of those problems where we're not given actual values to plug in to find something. We're trying to prove a relationship. And so basically, given this diagram and the information that we know from chapter 12, we want to prove that this relationship here is true. We want to find that. And so looking at the problem, we know that this is an elliptical orbit. And so we start with this equation here for the radius 1 from the origin to B here. And we know what that equals. And then we can do a similar equation for the distance R0 here. And so I just replaced the A and the B, RA and RB with R1 and R0 from our equations. And then similar to the previous problem, we know that the angle from the origin to B to the origin here, that's 180 degrees. And so we can say that C cosine theta A equals negative C cosine theta A. And so replacing that, we can create that relationship. And then, like in the last problem, we can add these equations together, which gives us this. We have two of these, and these are added together. And then looking at what we're trying to find here, this equation, we're getting pretty close here on the left-hand side. And so what I did was just divide the 2 over. And then this right-hand side of the equation here matches with this. And so now all we need to do is prove that GM over H squared is equal to 1 over rho. And so to do that, looking at this problem here, we have to recognize that at A and B, we are normal to the path and in the acceleration. So what that tells us is that acceleration normal is v squared over rho, which we know that relationship. And because it's normal to the path, we can set it equal to h squared over r squared over rho. And so this h squared over r squared is equal to v squared. And then from there, we can take our equation for gravity with big G and the force in the normal direction and set it equal. And then setting these two equations equal here, there's a lot of things that can cancel out. The little m masses cancel, the radius is squared cancel, and that just leaves us with gm equals h squared over rho. And then all that's left to do for this problem is to solve for rho. And so looking at, we want 1 over rho on this side, and so solving this equation for 1 over rho, we see that it actually equals the right-hand side of our equation here. And so replacing that with our 1 over rho that we just proved, gives us this equation here, which matches what we were trying to find. And so that is the solution for problem 9.